Hey guys, this is Mr. Mahmood, and you're watching the first and only lecture on this little mini unit with experimental design. In this lecture, we're going to cover a lot of the basic terminology dealing with types of variables, the difference between independent and dependent, relating a variable to a constant. We're also going to get into proper formations and proper formats in a good hypothesis, as well as making sure you understand you have variations in the different levels of your experiment with control and experimental groups, and then finally figuring out ways to really put it together in a professional and concise manner using data tables and graphs properly based on the types of experiments that you're dealing with. So experimental design is very, very important, not just for biology. Of course, we're going to be dealing with multiple experiments throughout this year. It's very important that you not only know how to set up your experiment yourself, but you can analyze an experiment well and put together proper results. But beyond just this school year, hopefully you've already had a strong background of experimental design, especially if you're coming from a Plano school. A lot of the terminology and the basic formatting here should probably be a review for you. And of course, it's also going to be very important for your further science classes besides biology when you continue to move on in your scientific career. But really, I want you to get past the idea of your science class, and I want you to get past the idea of the classroom in general. Proper experimentation is a critical skill that will give you all kinds of success in whatever sort of career path you move into. Whatever it is you plan on doing when you grow up, you're going to be faced with challenges. You're going to be faced with obstacles and problems. And if you know how to set up proper experiments and you know how to analyze problems properly and really figure out ways that can be practical solutions and ways to test those solutions out, you can easily overcome any kind of obstacle that gets thrown your way. So true understanding of experimental design will be one of those things that kind of stays with you for the rest of your life and you're able to use over and over again with unlimited success. So I take experimental design very seriously with my kids, and I really hope that you'll see it in that format as well. Okay, so to really get into a basic understanding of everything we're going to talk about, I'm going to try to incorporate as many examples as we can and just kind of walk through the basic format. It's pretty straightforward. So when you deal with an experiment, it's very important that you know how to properly set up the experiment to get valid results. I use the word valid quite a bit in this lecture, and validity is just the ability to repeat results of an experiment over and over again, to be able to conduct an experiment and get the same results over and over again. And it really increases the validity of an experiment. If something is considered valid, it can be tested by multiple scientists in multiple labs, multiple different scenarios. As long as they follow your exact procedures, they should be able to get the same results over and over. And those are the kinds of results that are really well supported and that are really well trusted in a scientific community. So I think the best way to talk about validity is to maybe talk about a non-example. So let's talk about a bad example of an experimental setup. There are multiple tests being done about the health factors and the benefits of dealing with many different types of oil, olive oil in particular. There was one research study that was done out of Australia where they actually went out on the streets and they stopped numerous random adults and started asking them questions about how much olive oil they take in on their diet on a daily basis, and then they compared that to how many wrinkles they had on their face, and they did a very detailed analysis of their skin and identified kind of the level of wrinkles and the depth of the wrinkles that they had. And the results that they came out with, doing the data, they identified a high majority of people that said they have a high amount of olive oil in their diet were very healthy in terms of their facial features, had very little wrinkles. So they came out with the results and said, you know what? Olive oil will cause you to have fewer wrinkles. You'll get less wrinkles with olive oil. And they came out with that result and sent it out. Now, what do you think's wrong with that experiment? There are tons of things that we can say are wrong with that experiment. But one of the key factors that we're going to be referring to here is variables. And in a proper scientific experiment, there should only be one variable at the beginning of your experiment. That one variable is the variable that you are, as the experimenter, are setting up. And it's the variable that you are going to be testing in terms of how it affects the results. So in this experiment, do you really think the experimenters only focused in on one particular variable when they were looking at these factors? Is the amount of olive oil intake that they might have, or what they tell you they might have, really the only factor that could determine the wrinkles on your skin? Absolutely not, of course. I mean, there's so many other factors that go into play, other types of components in your diet, the other kinds of things you eat, whether you're eating fast foods at McDonald's every day or whether your diet really is purely natural, organic, and you take a lot of responsibility and a lot of pride in the things that you eat. You could also talk about factors like whether or not you smoke, whether you work indoors or outdoors, poverty levels, all those different factors play very important roles in how you take care of and what kind of exposure you put your skin to that could all affect whether or not you develop wrinkles. So because there are so many variables there and there's no controlled experiment whatsoever, just to ask whether or not they take in one thing and to assume that that one thing is the reason for the result you're looking for, which in this case is wrinkles, is completely absurd, and hopefully you understand is a horrible, horrible setup for an experiment. So let's use this as a segue to talk about what variables are and what constants are, how you compare the two, and why it's so critical that you only really have one variable at the beginning of an experiment. So when we talk about a variable compared to a constant, by definition a constant is something that stays the same, and a variable is something that changes. Now, in a proper experiment, you want to set up as many constants as you possibly can. In an ideal experiment, absolutely everything is constant throughout your time where you're collecting data in your experiment, except for one thing. And that one thing is the variable that you as the experimenter set up on purpose at the very beginning of the experiment. That is what we consider the independent variable. The independent variable is the variable that you as the experimenter set up at the very beginning in order to test the effect of that independent variable on whatever it is that you're looking to measure. Okay, so here's a scenario. Here we have 4 flower pots represented. Now, you notice how the flower pots should be identical to each other because of trying to control the constant. So there are many different basic plant experiments that we can talk about. We can talk about the effects of water on plant growth, how light intensity and length and duration of light exposure affects plant growth. We can talk about temperature. There are many different factors that you can focus in on to see how plants grow, but they all basically require that you keep everything else constant. If I had many different types of plants and I was doing a test varying different amounts of water that I pour into those plants, and I just purely looked at the results of growth, that wouldn't be a valid experiment because different plants absorb different amounts of water. The roots, some roots are very good at absorbing water and they absorb high quantities, which means they'll grow more even if there's not as much water being brought in. So there are all these different factors that you have to try to eliminate as much as you can in a proper experiment. So the independent variable would be something that you introduce at the beginning that's different from absolutely everything else that's constant or remaining the same. So in this case, if I was testing the effect of water on these plants, I need to make sure it's the exact same type of pot, the exact same flower, the exact same amount and consistency of soil, concentration of chemicals in the soil, exact same amount of exposure to sunlight, temperature, everything else has to be constant. And the only thing I'm changing is maybe the amount of water that I'm giving to that soil and letting that soil and the roots of that flower absorb each time. Only then can I really get an accurate result and say that, okay, well, what I'm looking for in terms of measurement, or what we consider the dependent variable, that measurement that I'm looking for as a result of the independent variable, is it really truly because of the one independent variable that I introduced? And if it is, then that's something that we consider valid, accurate, and something that hopefully can be repeated many times if you follow the same instructions. So the independent variable is what you introduce at the beginning, and it should be the only variable at the beginning of the experiment. And then the dependent variable is what you're going to be measuring, whether it be just one time or multiple times along the way of your data collection, as a result of the independent variable. So any changes from one flower pot to another should be purely due to your independent variable, and then you can relate that and discuss that in your findings, your both graphic findings, and then in any kind of a written conclusion that you might be writing. Now, once you've identified the independent and the dependent variable, now you can start talking about a hypothesis. Now, a hypothesis is the experimenter's statement or estimate of what they assume to be a result of their experimentation. Now, you can't really have a proper hypothesis until you first have established your variables, especially the independent and the dependent. Now, once you have those two, it's very important that you include both the independent and the dependent variable in your hypothesis. A lot of times, teachers might encourage you to use what's considered the if-then statement, where basically you'll say, if the independent variable, then the dependent variable. Or what I mean by that is you state out if you do a certain thing that you're doing on purpose is the only variable at the beginning of an experiment, then this is the expected result and measurement that you're looking for, or that you'll expect to find. So for example, my watering of the flower pots, my independent variable being the amount of water, that would be in the beginning part of my if statement, and then the dependent variable would tell me, or would be my prediction of how that amount of water may result in terms of growth for the plant. So it's very important that you try to get as specific as you possibly can. Now again, the formatting really depends on the teacher. I don't really make too much of a big deal out of being that if-then format exactly, but it is critical that you consider a few basic components. There are some basic rules about hypothesis. One, it needs to be specific. And two, it needs to be testable. It needs to be something that you can actually go through an experimentation for and come up with a pretty consistent answer of yes or no. Yes, the hypothesis is true, this seems to be supported, or no, the results do not support my hypothesis. So again, as long as you're incorporating both the independent and the dependent variable in your hypothesis, it's usually a good place to start. So something along the lines for this experiment for the water, if a pot was given higher amounts of water daily, then there will be a higher plant growth as a result. Just because you make a hypothesis should never suggest that you are hoping for that goal, because it's very easy to have something called experimenter bias. Experimenter bias is when you want a certain result to come from your data, and you want to see some sort of massive end result. But a lot of times when you really want something to happen a certain way, you might not do things exactly the way you're supposed to make sure you're getting valid results. You may really try to skew the results, even subconsciously, so that the results you're getting are what you wanted. This is a major problem. This happens all the time with science fair participants, because they come in with this expectation of this massive result that they want that's going to change the world. So they really want their test to show up a certain way, and a lot of times it doesn't. A lot of times they're surprised by what happened. It didn't do what you wanted it to do, and now you're worried that your final conclusion and your data won't be that impressive. And so if you manipulate your results in any way, and you let your bias take control, then you've lost validity of your experiment. So it's very important that when you set up a hypothesis, when you talk about this prediction, you're not necessarily hoping for that result. You're simply saying what you predict to happen, and then just let the experiment run its course and use that data and really analyze that data properly and all data to put together your consensus from what you collected. Okay? Alright, so once you've identified your hypothesis, you already identified your variables, now it's important you talk about the levels of your variables. And to really emphasize the importance of that, let's talk about another bad experimental setup. In Europe and really all throughout the world, one of the major components of health and types of oils that they've been talking about having major health benefits, we're staying on the oil theme here after olive oil, is fish oil. Fish oil are polyunsaturated fats. There are many proper experiments out there that do suggest many health benefits of these types of fish oils, and possibly taking them as supplements. But this one experiment in particular had some flaws. In this experiment, they gave fish oil pills to about 1,000 students. I think it was like middle school students over the course of a year. They measured their scores on particular tests at the beginning of that experimentation, and then they gave every one of these kids massive amounts of these fish oil pills. They took about 6 of these huge pills per day, and then a year later they had them take certain levels of cognitive tests for that progression of the age, and they compared the results they had to what they predicted the results would be a year before. So what do you think's wrong with that experimentation? Yeah, many things. So we've talked about the variable thing. It's very difficult to eliminate every variable in that scenario, with the exception of those fish oil pills. Kids are coming in from many different levels. That progression in 1 year can be completely different from one kid to the next, even if they may have scored about the same on that whatever that cognitive test was when they started the experiment, right? So there are many problems there. But the biggest problem here is that they gave everybody the same test. They gave everybody the test and valued results no matter what might have happened had they not had those same pills. So it's very important in any experimentation, even once you set up the variables, it's important that you always have some group that isn't doing what you're expecting it to do and isn't being given your independent variable in an extreme form, so that you can always compare whatever results you're getting in that group that you're really testing out to the group that maybe is much more normal. So this is where we talk about the difference between a control group and an experimental group. A good example, again, we'll refer back to this plant growth scenario. If I was just testing the different amounts of water in growth, and every single one of them got some sort of a drastic amount of water that is maybe not really what you'd see in a natural environment, and I said, okay, yeah, they all had some kind of growth, and I can just measure that out and put it out, then even though, yes, there may be a difference in the growth between them, I can't necessarily say that growth wouldn't have occurred had I not done this extreme test. So it's always important to have something called a control group. A control group is exactly the same, 100% the same in the experimental setup as the other groups that you've had established for your experiment. But the variable that you're introducing is at its normal levels within a given environment. So when I say normal levels within a given environment, that depends entirely on what the test and your independent variable may be. A lot of times when we do an experiment on temperature, we use what's considered either body temperature as the control group, if it's something that's in the normal human body and you're testing something out that would live normally in the body, or if it's something that's basically occurring in a lab, a lot of times you're just dealing with what's considered room temperature, which is usually somewhere in the 20s for Celsius, lower 20s for Celsius, or somewhere around 70 to 75 degrees Fahrenheit. That's what we consider the control. It can be pH values, depending on the environment we're talking about. A lot of times the pH control will typically be neutral pH, which is distilled water. So the control group is the group that you're doing everything else the same with all of your crazy tests that you're running, but it's the one that's most like the normal environment. So if, in this case, there is some plant growth even in the control group, then you can say that not all of the growth that's going on with these other plants is purely because of what I'm doing to it, because there was already some natural growth occurring. So a more valid way of conducting that same test with the fish oil and the students will be to at least have a group of students that aren't taking the fish oil or taking something that we consider a placebo. A placebo is something to sort of manipulate the thought process of the subjects so that they don't know whether they're actually the control group or the experimental group. And that has a lot of psychological effects and benefits for the experimenter, because a lot of times if you're taking a pill for something, you may improve just because you're being told that that pill is going to help you. And so there's a lot of psychological play that goes into whether or not something is really helping you or affecting you, or if it's just all in your head. So if you give somebody a pill and tell them it'll help you just as much as someone else, and only one of you two is actually getting the medication or actually getting that oil to be tested out, and the other one's getting sort of like a sugar pill or just water solution or something like that, and they don't really know the difference, then it really can be more accurate to see how the two progress, and if there is a significant change from one to the other, then it's much more likely that you can say it's because of the experimental group and it's because of the variable that you introduced. Again, there are a lot of valid experiments out there that do suggest olive oil and fish oil have major health benefits, but these two that I'm talking about in particular, just weren't set up very well. So in any given experiment, it's very important that you not only are testing out your independent variable in all these different extremes, but it's also very important that you have a control group that doesn't have that sort of extreme. So you can compare your dependent variable, whether it's growth or whatever the measurement of change is that you're looking at, and you can always compare that to the control group and make sure that the real change is because of your independent variable, not just because of the natural events that would have happened had you not introduced the extremes that you did. So once you have an understanding of all these basic components, then you can talk about a proper experiment. And then you can sit down and you can run the test, you can let the data speak for itself, and now it's time to start talking about collection of your data and then organization of your data. So the basic components usually when we talk about graphical representations for any given sized experiment are in the form of a data table and a graph. Now a data table can come in many different forms, but a lot of times we tend to encourage certain consistencies in terms of a data table. A lot of times that first column, or the column there on the left, we would encourage to be the column representing your independent variable. So whatever it is that your independent variable may be, you would represent it there in that first column. So the top left, any sort of top line of any data table should be where you have your labeling and you're explaining what's going on within that column. So that's where you'd represent what your independent variable is, and if there is any sort of units for your variable, you'd include it in that point as well. And then from that point underneath, you have your different levels of your independent variable. Now the levels are all the different tests amounts that you were doing for that experiment. And again, you should always make sure that one of those levels is considered your control, so that you have something to compare everything else to. So that first column is what we call the independent variable, up and down. And then the dependent variable would be anything from that second column over. Now, depending on the experiment, the dependent variable could be a single measurement, and in that case, your data table is just 2 columns. If it's multiple measurements being done at one time, then it could be multiple columns. And a lot of times, if you really want to set up comparison results from one level to the next, if you do have multiple measurements for your dependent variable, it's often a good idea to come up with a final column that we consider the average column, so that that's a single value for each variable that you can turn around and discuss much more easily than talking about all of these different variations that might have occurred over the course of your experimentation. So the dependent variable is everything to the right of the independent. Again, you have the top row to be represented as just the labeling of your dependent variable. Again, any sort of units that may be involved in the measurement, include that in the labeling. If you include labeling of units in that top row, then you don't have to sit there and rewrite the unit every single time when you're writing your data. You can simply write the numerical values, and it's assumed that if it's in that column, then it's in the same unit that's being represented at the top. It's also critical to always set up a title for your data tables and your graphs and any sort of a graphical representation. It's a basic rule of thumb for science, because if you wanted to turn around and publish your results, you had some sort of miraculous result, something very interesting that you think people outside of your classroom or outside of your school may be interested in hearing, and you want to try to publish, a lot of times they'll simply take segments of your experiment included in certain articles or included in other people's research. So it's very important that if they take your data table, that they know what's going on, and your title should be a clear representation, pretty straightforward, of what you were testing. And that's why your title, just like your hypothesis, should always include both your independent and your dependent variables. So just at a glance, anybody can look at your data table and say, okay, I get the basic idea of what you're trying to test here. And then finally, when we talk about graphs, there are 2 general forms of graphs that we talk about here, at least here in biology. You can extend off when you get a little more detailed with statistical analysis and scatter plots and different types of variations of how you graphically show your data. But usually, at least here within the biology scenario, any sort of graphs that we expect you to do will fall into one of these 2 general categories. They're either considered bar graphs or histograms, which you see here on the top, or line graphs, which you see on the bottom. Now, the basic difference between the 2 is whether your results are being measured on that exact moment in that single occurrence for any given experimental setup, or if you're setting up an experiment, letting it run, and then taking measurements along the way. So it's really, a lot of times we relate line graphs, what you see there at the bottom, to measurements in relation to time. So a lot of times, we'll start with a line graph there at the bottom. If you're setting up an experiment and then you're adding certain amounts of things along the way, and then you're measuring something happening over that period of time, let's say there's a consistent drip of water in a flower pot, and that drip is not changing in any way over the course of maybe 5 days, and then each of the 5 days you're taking measurements of the growth that's occurring within the plant, that would be something that you can consider continuous, because the key here is from one point to the next. If it's continuous, then you can assume that if you were to make a measurement at some point in between the 2 that you actually did, it should fall somewhere in a line between the first and the second, because it's the same scenario the whole way through. So if it went from 1 to 2, then if you were to measure it halfway in between those 2, it should be a value of 1.5, because it's continuous. Now, if you're not doing that and you're just getting a single measurement or a single value for one experimental setup compared to another, you can't make any sort of assumption about what might have happened in between. Assumptions are things you want to avoid at all costs in experimentation, with the exception of possibly your hypothesis before the experimentation occurred. So if you're doing some sort of a setup where each individual experimental group compared to your control group was given a different variety of your independent variable, and you're only really getting one measurement for that, so like if I had multiple flower pots, each flower pot got a different amount of water daily, I can't make any assumptions about what would happen if I put some sort of interval in between of water each day in a different hypothetical flower pot. So I can only give my results for each individual scenario, each individual flower pot. So in that case, we're dealing with a bar graph or a histogram that you see on the top. So that's where you just measure the results, you just plot them one time, and that line represents sort of just a visual effect of how they compare to each other. For both types of graphs, it's the general rule of thumb when you're dealing with the types of variables. Your independent variable is usually going to be your x-axis. So the independent variable is your x-axis, and the dependent variable will be your y-axis. So starting with a bar graph, if you have the flower pot and the amounts of water that was given to each one, your x-axis would be the amount of water added to each plant, and your y-axis would be maybe the growth of the plant in a certain unit of measurement, millimeters, something like that. For a line graph, the only variation is a lot of times that x-axis is time. So time could be anything from seconds to days to months, depending on what your experimentation might be. And then the y-axis is usually the dependent variable, or the growth that you're looking for. And again, just like a data table, you always want to make sure you have a proper title above any sort of graphic representation. So always make sure you have a title above any sort of graph for the same reason of publication. You always want it to be able to be taken with you, and typically I don't have any problem with the title being the same as the title for your data table. Always include an independent and a dependent variable within it. So that's pretty much it, guys. As long as you incorporate all of those things, then you have a good chance of setting up a valid experiment. Always try to avoid any sort of experimenter bias in any way you can, because you really want to see the true results of this experiment, not necessarily what you're hoping for, but if something is going to come out the way you might have been expecting. And if that's not the case, usually scientists flourish and really gain from errors and mistakes and incorrect assumptions more than we gain from what we thought already to be correct. We learn a lot more from our failures, hypothetically, than we do from our successes. So that's always what kind of keeps science moving and keeps us motivated to constantly want to find new solutions to new challenges and figure out ways to overcome obstacles. So again, experimental design goes way beyond the classroom. I hope you understand the basic components, and I hope you utilize these things for the rest of your life in your continued and future successes. Alright guys, thanks for watching. I'll see you next time.